All right, example 6. This gets us back to these heading slash bearing problems. This one only has heading in it. Airplane is traveling with an airspeed of 320 miles per hour and a heading of 62 degrees. A wind of 42 miles per hour is blowing in a heading of 125 degrees. Find the ground speed and course of the airplane. So this is a vector addition problem related to what we did in Algebra 2. All right. Problem though is heading 0 degrees is up here. We go this way. Vectors 0 degrees here. We go that way. So what we have to do is we have to draw a heading picture, convert it to a vector problem, solve it as a vector problem, and then go back to a heading answer. So it's kind of a weird thing going on here, but that's what we're going to be doing. So if we take a look at what's going on with this airplane, if I draw a north-south line, I always start with that with the heading and bearing. And I'm going to put the plane's position, let's say, right here. All right, the direction and speed of the plane is going to be the plane's vector. The direction and speed of the wind is going to be the wind's vector. Adding those vectors together gives us the actual direction and speed of the plane, is what we're trying to find here. So, two vector forces are affecting this travel. I'll do the plane in black and I'll do the wind in, I think wind feels like yellow to me. So we're going to make a yellow wind and a black plane vector. So the heading of the plane is 62 degrees. So straight up is 0, 62 degrees would be kind of off around that direction there. And again, 62 degrees being measured from the north clockwise to the vector. And I just decided the vector of the wind is going to be purple instead of yellow because I have a purple marker. Actually, I guess it'll be yellow, but it doesn't show up very well. All right, so that's the plane's vector. The wind's vector, and the speed is 320 miles per hour. Let's put that on there also. So 320 miles per hour. So the magnitude of the plane's speed is 320, and the direction of the plane is 60 degrees. That's what they're actually purposely trying to fly right now. Right? Then we have the vector of the wind. There's my purple. And it's blowing 42 miles per hour, so obviously it's not going to be as long. So this is 90. 125 would be another 45 degrees beyond that, so about here. Let's go about like that. And that's going to be 125 degrees. Like so. So there's our picture of what's going on in this problem in heading form. Now I want to go to vector form. Oh, and this was, of course, 42 miles per hour. So if we go into vector world, I'm going to get rid of this line here. And now I'm going to draw a horizontal line through there like so. And you know what, I'm going to put the vertical line back in there too. So if I superimpose an XY axis on this thing, the vector is going to be length of the vector and then angle from 0 counterclockwise to the vector. So if I'm looking at this one, of course this is 0 degrees here, and we're going this direction to get to my vector. If that's 62, this is going to be 28 degrees. I'm feeling like that's not drawn very well to scale, but oh well. We can live with that, I think. You know, I'm going to use maybe a different color here too. Let's go red. So we can see where the original stuff comes from. Okay. Looking at this vector, if that's 90 degrees, this is 35 degrees right in here, which means if I go around this way, this is going to be 325 degrees. So looking at my vector addition problem I'm trying to create, then my plane vector in polar form is 320 miles per hour at an angle of 28 degrees. We're adding that to an angle, or sorry, magnitude of 42 miles per hour at an angle of 325 degrees. So take the heading information to create a polar vector problem. Vector addition is what it was in Algebra 2. We're going to change both of these to IJ form in order to add them together. We're going to go back to polar form to get the answer. And then we've got to go back to heading form. All right, so if we take a look at the first one, this one. If I do 320 cosine of 28 degrees and 320 sine of 28 degrees. It gets me the horizontal and vertical components. So this plane vector is 282.54I plus 150.23J. And if we look at the wind vector, we're going to be adding to that 42 cosine of 325 and 42 sine of 325. So we're going to get plus 34.40I, and we're going to get minus 24.09J. And that gets me a resultant vector. If I add them up, that's going to be 4, 9, 6, 1 carried, 316.94I. And these are going to subtract 126.14J. So looking at the wind, and just considering the wind the way it is, the horizontal and vertical components here. So the plane is flying horizontally some speed and vertically some speed to create this heading that is actually going 320. And the wind is blowing horizontally some speed, vertically some speed to create this, right? So they're both going the same horizontally, so the horizontal components add to make a bigger horizontal component. But the vertical components are going against each other, so they're subtracting. So they kind of get a visual of what's going on in the problem. That's what the component form does for us. But we do get this final horizontal and vertical component here. So then we want to go back to polar form. So step 1 is the magnitude is equal to the square root of the sum of the squares of these two things. So 316.94 squared plus 126.14 squared. 316.94 squared plus 126.14 squared comes out to 341.119. So 341.12. And that's the actual speed the plane's going to be flying. So the plane itself was supposed to be flying 320. It's actually going 341. It's going an extra 20 miles an hour because the wind, again, is pushing horizontally some, even though it's going against it vertically. Horizontally, it's actually pushing it faster. Step 2, alpha is the inverse tangent of the vertical over the horizontal. So 126.14 over 316.94. So inverse tan of that. And that comes out to 21.70 degrees. Which means step 3, theta, again in polar form, vector polar form here. We're in quadrant 1, right? Because we got positive, positive. In quadrant 1, theta is equal to alpha, so 21.70 degrees. So our magnitude and direction vector-wise in polar form is 341.12 at an angle of 21.70 degrees. So if I were to just draw a picture of this, so I'm going to erase all of this and just draw a picture of our final vector. Let's do this. Perfect. So our final vector, the plane's going a little bit faster and a little bit further south, right? Closer to south, so more east. This is the 21.70 degrees, 21.7. And this is 341.12 miles per hour. But in heading world, 0 degrees is right here, and we're trying to find this angle. So use properties of right angles, use straight lines, whatever facts are in there to figure that out. But if I want to determine how big that angle is and know how big this angle is, I have the ability to figure it out, right? So 90 minus that, it's going to be 68.30. So speed and course. Course would be a heading, all right? So the answer is 341.12 miles per hour on a heading of 68.30 degrees.